What we're looking at is going to be limits as far as dealing with infinity is concerned. Two different ways of looking at this. One of them is what happens when a limit is infinity. Well, I've got this equation right here. F of x is equal to x minus 3 over x plus 3. And the key to what's happening is what is happening around 0. Where do we get hit 0? Where do we start turning negative numbers and positive numbers? In other words, where do we have positives divided by negatives? Where do we have negatives divided by positives? Well, in the numerator, this changes at 3. Now, for right now, this is going to be a little bit less important when compared with talking about the denominator. X equals negative 1. At and up to negative 1 and adding up to 3, we're looking at where the actual sign of f of x changes from positive to negative and negative to positive. Try to get to more of my head's on the screen. Looks weird having a headless person talking to you. So at this point right here, let's think about what's happening. If I plug in a number that's less than negative 1, let's say negative 2, I end up with a negative over a negative, which is positive. So all of my function values within this interval from negative infinity to negative 1 are positive. And then if I come over here greater than 3, I'm plugging in numbers that are greater than 3. So that gives me positive. Of course, a number greater than 3 added to 1 is also going to be positive. So from infinity to, no, that's impossible. From 3 to infinity, now you're looking at something that is going to be positive. So my function has positive values everywhere up in here. 0 gives me a negative over a positive, which is negative. So within this interval right here from negative 1 to 3, now I'm talking about negative values. So from negative 1 to 3, everything is going to be negative. Now, nothing really fancy happens here at 3. If I plug in 3, I get 0 over 4, which is 0. So at 3, my y value is 0. The neat stuff happens here at negative 1. At negative 1, and we start talking about the limits, when we're here, and let's just try, for instance, negative 1.01, and then let's try negative 1.001, and then let's try negative 0.99 and negative 0.9 to see exactly what's happening here. So when we're here, we are 1/100th away from negative 1 in the denominator. So we end up having the arithmetic of negative 1.1, that's going to be negative 4.01 over, and then it's going to be a negative value here, right? So negative 0.01, which gives me a number around 400. Negative over negative is positive. So we're talking about a very high number right here. Well, the numerator does not change too terribly much here, neither does the denominator, but the actual division portion changes a lot when I talk about plugging in this negative 1.001. So I've got negative 4.001 over negative 0.001. And now when I do this arithmetic, I get a number that is really close to 4,000. So it's this changing, the numerator change is very insignificant. This denominator's change going from 1/100th down to 1/1000th is where the huge change is. So now we're talking about when I graph it, it's going to be way up here somewhere. Can't quite plot it, but that's what's happening. And I'm sorry, I should be at -190. I was trying to graph it close to here. So we're way up here. Now, when we just jump a little bit over here, now I'm talking about, well, I've got -0.09 with this, so this is -3.99 over with a negative point, well, let's do 0.9 first. -3.9, and then right here, that's going to be divided by, where am I? Here. So I've got -0.01. No, -0.1. So that becomes 39. But this time, I'm looking at this value being negative and this positive, so it's actually a positive 0.1 this time. So when we do this arithmetic now, just by barely changing this value right here, I go from being negative to positive, which changes the overall value of this function. So we're down here, in this case, here. And then we move to -0.99, which is a little bit closer to this -1, and we get -3.99, but this time we're over 0.01. So this gives us 399. So we're way down here. And we end up seeing that we have a vertical asymptote here. Now, horizontal asymptote, if you remember, you compare the degree in the numerator with the degree in the denominator. Both degrees are 1, so you use the ratio of the leading coefficient, 1/1. So we've got a horizontal asymptote at x equals 1. Sorry, that would be y equals 1. All right, so my graph takes along this shape here. Now remember, we got to cross through this point here. Also, if we plug in 0 for x, we get -3, so the graph crosses through right here. So we end up with our vertical asymptote here as we approach -1 from the left. We get infinity. As we approach -1 from the right, we get negative infinity because it's decreasing without bound there. Now, in this case right here, remember, we said for a limit to exist, the left-hand limit had to be equal to the right-hand limit. Well, infinities don't equal to each other, but if we see that both limits are infinity, we say that the limit is infinity. Infinity does not exist, but infinity is something that is specific. If we can picture what's happening, if we say our limit's infinity, we know that it's growing without bound on both sides of it. In this case, it's not. In this case, the limit does not exist because these two values, even though they can't be equal, they don't look alike. They're totally opposite of each other. So, for this reason right here, we say that the limit does not exist, and our, again, right-hand limit's negative infinity, and our left-hand limit is positive infinity. Going a step further with this, let's talk about this infinite limit. We talked about this horizontal asymptote just a second ago. We said that it's at y equals 1 because we compared the degree in the numerator with the degree of the denominator, and we looked at the leading coefficients. The bigger numbers we get to plug in for x, the less and less significant this -3 and +1 is. If I take 0 and subtract 3 from it, that 3 has a big effect on it But if I take 1,000,000 and subtract 3, very little significant impact on it. So we end up with, like, if we plug in 1,000,000, essentially it's a ratio of 1,000,000 over 1,000,000. If I plug in negative 1,000,000,000, it's essentially negative 1,000,000,000 over negative 1,000,000,000. So that's the reason why we hit this ratio of 1. That's the reason why we have this horizontal asymptote. It never will actually equal to 1 because we still have this negative 3 and 1 here that's just keeping it off of 1. But it gets microscopically close to 1. In fact, we can get it as close to 1 as possible. That has to do with the epsilon delta definition of the limit, saying that, hey, we can get as close to a value as we want to if the limit does exist there. So in this case right here, we've got this limit to be 1. So that is our horizontal asymptote. In the event that this had been a higher degree in the denominator, now all of a sudden the denominator gets a lot bigger, a lot quicker than the numerator does. Therefore, that would have a limit at 0. So you would have a horizontal asymptote along the x-axis. And if our numerator's degree is greater than our denominator, the limit does not exist, and we start talking about having oblique asymptotes there. So this is a little bit of a look at what an infinite limit looks like. A few things to check for in an infinite limit is, first off, where are we changing sides with the numerator and the denominator? But even more specific than that, we want to see what happens after we simplify it. A function's still not defined if the denominator is ever equal to 0, whether it's simplified or not. But this asymptotic behavior only happens when you start talking about having that denominator that is equal to 0. So hope that this helps you. Again, your assignment is going to be on the board for you to work. I'm sorry that I'm having to miss this day. Odd answers are on the back of your packet, so make sure you check and make sure you're getting them right all along. If you need to discuss any of these answers with a neighbor, do so please, and I will see you soon.